So continuing on with the normal distribution, the normal curve. The standard normal distribution is a normal distribution that has a mean of 0 and a standard deviation of 1. If you recall, that's kind of what happens whenever we calculate z-scores. When we calculate z-scores, it transforms the mean to 0 and the standard deviation to 1. And if you recall, whatever the shape of the original distribution, the shape stays the same. So if we have a normal distribution that has a mean of whatever and a standard deviation of anything, could be IQ scores, heights, whatever, then the standardized variable, when you calculate the z-scores of every single one of those points, if the original distribution is normal, then the z-scores are going to be normally distributed with a mean of 0 and a standard deviation of 1. So this standard normal distribution is a very common distribution that we work with in statistics. Because of the 68, 95, 99.7 rule, we can find percent of values bounded by certain cutoffs, namely 1, 2, and 3 standard deviations. However, what if we want to find other percentages? For example, suppose we have a standard normal distribution, and we want to find the percentage of the data points that are larger than 1.5. In order to do this, we need to use a calculator or an applet or something along those lines. So the calculator function we're going to be working with is called the normal cumulative density function, abbreviated normal CDF, and it works like this. You simply put in the lower bound z-score and the upper bound z-score, and this calculator function will calculate the area in between them, which represents the percent of the data points between the bounds. This is an AP testing tip. In order to get credit when you're taking the AP test, you have to show a sketch, you have to explicitly identify the mean and standard deviation, and you have to identify the lower and upper bounds. So there's actually 5 things there that you got to get. All right, so let's find the area above 1.5 standard deviations above the mean. All right, so let's start with a sketch. It can be a very rough sketch, doesn't have to be super accurate. Let's put down the mean. Let's put down the standard deviation. So I like to, basically measure the distance between I mark the standard deviation as that distance between the center and that point of inflection. It's a nice place to put it on the graph, makes it easy. And I don't have to label a whole bunch of tick marks. And then I got to label the cutoffs. So I want to go from 1.5, which is about here, and I want the area to the above it. So the probability that z is greater than 1.5 equals normal CDF. I'm going to put in the lower bound of 1.5 and the upper bound, which is infinity, because I want to go all the way up forever and ever. Menu, statistics, distributions, normal CDF. So there's the function on the calculator. We'll do it again so you can get it down, but 1.5 to upper bound of infinity. This is kind of a nice little calculator window that helps us. And as you can see, the default is the standard normal curve. Just to let you know, you could actually just type in norm CDF. You don't have to use that, go to the menu. And you don't really need to put in the mean and standard deviation. If you just do 1.5 to infinity, that'll give you the same thing. So 0.668. This is 0.0668, also known as about. I guess that's 7% or 6.7%. There's my area. There is a bit of a shortcut I believe that you can use on the AP test. You don't necessarily have to do a sketch. I think this gets you full credit. If you say norm CDF and then you say lower bound equals 1.5, upper equals infinity. That's a terrible statement. Upper, you should never use equals infinity, but for the sake of this, I think it's all right. And then mu equals 0 and standard deviation equals 1. In general, they don't accept calculator talk, but if you get this, it gets you credit for normal. when we draw the normal curve, that sketch gets us credit for stating that it's normal. So you could do it this way, or you could do it this way. I have to state the mean and standard deviation explicitly. Well, if you label those values here, you get credit for it as well. And then I have to state the lower bound and the upper bound, or the area you're looking for. And again, you can do that explicitly here and here. So if you were lazy, I think this gets you full credit, but I'm going to recommend that you do the sketch because it helps you visualize it. All right, so let's do some examples. Let's find the area on the standard normal distribution that's less than 0.54. So there's a probability statement. Sketch a curve, rough sketch, label the mean, label the standard deviation. Let's put our cutoff in there. 0.54 is going to be right around there. I want the area to the left of it, area below it. That gives me credit for everything right there. And the calculator command is menu, statistics, distributions, normal CDF, negative infinity to 0.54. 70.5%, 0.705. It looks about right. Looks more than half. 70% looks about right. That's it. You should be able to crank through these pretty fast. Draw the curve. Label the mean. Label standard deviation. So this is a z-score greater than 3.89. Holy smokes, 3.89 is going to be way up here. 3.89 and then to the right of it. So this is going to be a really small percentage. We should get a really small percentage. Menu, statistics, distributions, normal CDF, 3.89 to infinity. 4 zeros and a 5. That is 0.00005. Very, very rare. Yeah, just extremely rare. Between two values, okay, I do the same thing again here. It's getting a little repetitive, but practice, practice, practice. Mean is 0. Standard deviation is 1. And I want the area between 0.49 and 1.82. I don't know what that's going to be. Probably about maybe 35, 40%. Menu, statistics, distributions, normal CDF, 0.49, 1.82 was it? I can't remember. I think it was 1.82. 27.7 or 27.8. Yeah, 1.82. Oh, dope. 0.278. This is 0.278, about 30%. Equal to, oh, that's a typo here. Equal to 1.55, sorry. So what's that going to look like? Well, mean of 0, standard deviation of 1, 1.55. Well, we don't really need a calculator to find the area under a point. We know a point has no width, so there should be no area, so it should be 0. Again, what's the probability of getting exactly 1.55000000, infinitely many zeros? In a continuous distribution, that probability is 0, basically. The calculator will verify that. If you put in 1.55 to 1.55, it also gives you 0. So within 1.5 standard deviations of the mean. Mu equals 0. Sigma equals 1. So within 1.5 standard deviations of the mean, here's the mean. So I got to go 1.5 standard deviations to the left and about 1.5 standard deviations to the right. So between, here's my probability statement. negative 1.5 less than z less than 1.5. By the way, you could also write that as negative 1.5 less than or equal to z less than or equal to 1.5. Of course, these are going to be the same because probability of any that it's equal is 0. So menu, statistics, distributions, normal CDF, negative 1.5 to 1.5. It's going to be between 68 and 95, right? Because, yeah, 0.866. That is 0.866. The inverse normal CDF function. Suppose, these are nice if we have the cutoffs and we want to find the area. Well, what if you know the area and you want to find the cutoff? So instead of inputting z-scores and outputting the area, with this function we'll input the area and it will return a z-score. So the calculator function is called the inverse normal CDF. The inverse would be inverse normal. And beware of this, you always have to put in the left tail area to get the z-score out. So you can't put in the right tail area. What z-score has 25% of the area to the left of it? Well, let's draw it. Mu equals 0. Standard deviation equals 1. So 25%. So that's probably maybe right around there. It looks like about 25%. So the area to the left is 25%, and I want to know what's the z value that cuts that off. If I had to take a guess, I'd probably say, maybe around -1, -1.2. Let's just use the calculator to get a better approximation. Menu, statistics, distributions. Now let's use the inverse normal function. And again, we always have to put the area to the left. Keep these standardized. Negative 0.67. So my approximations weren't very good. So that z cutoff is negative 0.67. That's it. 33% of the area above it. Mean equals 0. Sigma equals 1. And I want 33% of the area above it. What is that z-score? Now, you cannot put in the right tail area. You have to put the area to the left. Since the area underneath the entire density function is 1, 1 minus 0.3 is 0.67. So I'm going to put the left area in, which is 0.67. And you could just type in, if you wanted, inverse norm, if you can just remember that, or if you think that's quicker. And you just need to put in the area, 0.67. You do not need to put in the mean and standard deviation. It'll default to the 0, 1. 0.439, 0.44. So the z cutoff is 0.44 positive. That looks about right. This is 0, this is 1. The middle 99%, or the middle 95%. Maybe we can just do one of these two. We've got a minute left. I should do this one. Now, normally you would say, well, I already know that the z-scores are -1 to 1. But remember that 68, 95, 99.7 rule was actually just an approximation, and not as good of an approximation as it could have been. Let me show you. 0, 1 standard deviation, or standard deviation equals 1. If I want to cut off the middle 95%, so I need a negative z and a positive z value that cuts off 95% in the middle. Now I could do this two ways. I could get this left function by putting in the left area. Since there's 5% on both tails, there is 0.025 on each tail. So if I want this negative cutoff, I could simply put in menu, statistics, distributions, inverse normal, 0.025, and that will give me the left cutoff. See, notice it's not exactly -2, it's -1.96. So this is negative 1.96, and this is 1.96.